So how do I learn new things? When I come across a new topic in physics, how do you learn it? The first thing I would do is ask myself, what is it? And ask myself, can I explain that to an 8-year-old? Can I explain this concept? What is a capacitor to someone who never studied physics before? And the answer is yes. A capacitor is very simple. A capacitor is basically a power bank, right? It's basically a rechargeable battery. So you've learned that it's something, we symbolize it like this, right? So you charge it up, and then now you can, once it's charged, you can plug it into a light bulb and try to power something else. All right. So the first, this is a device that stores charge. So that's all what a capacitor is. And now the quantitative concept that goes into your variables of your equations is capacitance, right? So what is it? The symbol. The first thing you want to learn is the symbol, right? Is C, and the next thing you want to know is its SI base unit, and the SI base unit is farads, right? So you can have picofarads or microfarads. If you have something like that in front, it's just 10 times some power to that farads. All right. So the first thing, can you tell an 8-year-old? All right. So now that you know what a capacitor is, it's a power bank. What is capacitance? Well, it's basically, so in simple language, it's basically something that, it basically measures how powerful, measures how much charge you can store. So that's the simple language, how much charge your power bank can store. So how about the second thing you want is go a little bit more technical, not just in simple language when you learn a new concept. So the technical definition is C, in words, is how much charge you can store per potential difference. So if I set up a certain potential difference across these two sides, let's say delta V, how much charge I can set it up, charge over here. So the idea is in equations. So the definition in the equation is the charge per potential difference. That would be like this, okay? All right, so let's go a little bit deeper. How we can, so first thing, learn how to explain it in simple language. Second thing, know the definitions of the things. All right, so now let me imagine I have a big capacitor like this. The way to solve the problems, what I like to do is always label all the charges on the plate. So if I put in, if I connect this to a battery like this, on the battery, it's basically a device. If you ask a chemist what a battery is, they'll give you a very complicated answer. They'll tell you about ions and ionizations and chemical reactions. But to a physicist, a battery is a very simple definition. It's something that sets up a potential difference. What that means is it will tell you that one side has a different potential than the other side. Okay, for example, if you have a 9-volt battery like this, it will say that, for example, if this side is 0 volt, this side is going to be 9 volts. The difference between this point and this point is going to be 9 volts. Okay, so that's what a battery does. So physicists, we don't care what's going on inside, just care about what's outside. So now, what happens? How do I charge up the capacitor? If I put a positive charge here, positive charge, as we learned from last week, always goes from high potential to low potential, right? Since you see a break over here, so the only way it has to go is it moves around this direction. So that's why all the positive charges will build up over here, but there's a gap, so it cannot go further. How about on this side? Well, this side is all, it starts off neutral, right? So it starts off with plus and minus charges. Everything is neutral along the way. It's a neutral wire. But as soon as you set up the potential difference and it accumulates all the positive charge here, what it will do is it will repel all the positive charge this way, and it will attract all the negative charge over here, and all the negative charges will start building up. So all these will move and build up on this side. So how much charge it will build up? It will build up exactly minus Q. And it cannot build up more than that because it is only plus Q over here. It will attract that much. And you cannot attract more than minus Q. If it attracts less than minus Q, it will keep attracting until it equalizes. All right. So how about what happens if we have things in parallel. We have a capacitor in parallel. How do we, what kind of new formulas we can learn from that? So what you can imagine is if you have a wire going through here, but instead of connecting it straight forward, try to split it in half, right? So instead of connecting straight to it, split it in half, and now take a pair of scissors and cut straight through like this. Okay? So initially, let me draw this over here. Initially, you have this situation, but now you can basically, by taking a pair of scissors and cutting it in half, you have this situation, like this. And initially, you have a capacitance over here. You accumulated minus Q and plus Q and minus Q with a certain potential difference across this point. Now you basically have something very similar to a lot of homework problems you've solved, right? So you have this potential difference across the first capacitor and the potential difference across the second capacitor, like this. So plus Q1 minus Q1 plus Q2 minus Q2. So immediately, the first thing you can see is basically these two should add up to this. So the first equation you learn out of this is Q equals to Q1 plus Q2. Right? Just because splitting this wire into two pieces and then take a scissors and cutting it through will not affect anything else, right? It's basically the same picture. Right? On the other side, you also see that minus Q is the same as minus Q1 plus minus Q2. Right? But that's the same thing, right? Minus Q equals minus Q1 plus minus Q2. Something the same that. How about the potential? So that's one formula that we can extract out if things are in parallel. How about the potentials? What can I say about them? So you see that this point is basically the same as this point, effectively. So also this point is the same as this point. So the potential difference across the first capacitor is the same as the potential difference across the second capacitor. So immediately we can extract this information out. Before I put a box around that, you realize this is the same as this, right? This point is the same as this point, right? And this point is the same as this point. So the potential difference across here is the same as the potential difference across here and the same as the potential difference across here, right? So all of these we learn is the same. And it's always one good thing is if you remember the definition of what a capacitance is, you can plug this into here and learn new facts about it. For example, if I plug it in here, V1 is basically Q1 over C1. It's equals to Q2 over C2. It's equals to the total, let's call it Q total over C total, right? Or the C equivalent, whatever you want to call it. Let me just keep it simple, like this. So imagine if I give you C1 and C2, and I tell you, let's say I tell you the total the battery around here. So if you know that, let's say this is 9 volts across this is connected to the battery, right? So if this is 9 volts, so you can immediately, you will be able to use the definition because you know the capacitance and you know this, you'll be able to find the charge stored on here. So if you know this, you will know all the other charges as well, right? For example, if you, because, right, let me fill in this side as well. If you plug in the definition of C into here, what do you get? You get C delta V is C1 delta V1 plus C2 delta V2. But you know that the potentials are all the same, so they cancel out, which gives you the formula that you use a lot in homework. C is equals to C1 plus C2, right? So yeah, so if you know C1 and C2, you will know C, and then you'll be able to, for example, looking at just the right-hand side of this, you'll be able to find Q2, and matching this with this or matching this with this, you'll be able to find all the information you need. Out of these three that is relevant for parallel, I wouldn't go ahead and memorize everything. As you see, the first two, I can extract pretty much directly from reading off the diagram. I can see that this is the same as this and this. And then here, I can read it off from looking at this is the same as this, same as this. So I won't go and memorize that, but I'll remember this because it makes solving problems much quicker. Okay. Let me quickly explain series as well. So if you learn how to draw these type of diagrams, like how I did, just a quick reminder, every time you draw a diagram for capacitors, always label plus and minus Q on both sides, label the delta V across each capacitor and label its capacitance, and then you'll be able to extract all the information you need. And you just need to memorize 1 or 2 equations. which makes things much easier. So let's say I have this capacitor as before, right, plus Q minus Q. But this time, instead of splitting it into parallel, let me just put a piece of metal in the middle and connect it with a wire like this. So I'm just literally putting a piece of, let me bold this a little bit, just putting two pieces of metal in the middle and connecting with a wire. It doesn't change. Now I built two capacitors out of this, but yeah, let me label everything. Q1 minus Q1 plus Q2 minus Q2. Okay. So immediately you can find a relationship that, for example, Q is this line, which is the same as this line. So Q is the same as Q1. Right? Can you see that? Q is the same as Q1. How about on the other side? Can we see another relationship with Q2? Right? On Q2, you can see that minus Q2 should be the same as minus Q, because all I did was insert an extra piece of metal. It's not going to change, right? It's not going to change the fact that it started out like this. So we also got minus Q is the same as minus Q2, which means Q is the same as Q2, which also means Q1 is the same as Q2. We can combine this together. And it should be obvious Q1 equals to Q2 because this was a neutral piece of metal. I just inserted an extra piece of metal in the middle. So if this side has minus Q1 amount of charge, this side better has plus Q1 amount of charge, right? So Q1 has to equals to Q2, right? So this is one equation. You see it's a little bit different from the parallel case because parallel is this is equals to this plus this, right? But I don't memorize all these facts because if you know how to draw this, draw these two side by side, draw the equivalent version and the split up version side by side, and then you can you can extract all this information. How about delta V? How about the potential difference? Can you establish a relationship between the potential difference between V1 and the potential difference V2? Well, you see that if let's say if this is 3 volts and this is 5 volts, if the difference between capacitor 1 is 3 volts, the difference between capacitor 2 is 5 volts, what's the total potential difference? It will be 8 volts, right? So this difference plus this difference is the overall difference. So I can figure out this as well. So this is another useful formula. Again, I don't memorize these, so I probably shouldn't put it in box. I'll erase it later. Now let's plug in the definition as before. Remember my trick. Insert the definition of capacitance into both and see what new information you learn because they are very relevant, very helpful in solving all the homework and quiz problems later on, right? So you plug it in and see what you learn. Q is CV, right? C delta V is C1 delta V1 equals C2 delta V2. So again, if you know, for example, if you know these two and if you know this, you'll be able to find V1 immediately. What do you learn from here? Again, I don't memorize these. You can figure it out. What will I learn here? Let me squeeze this up a little bit. If I plug this in here, I have Q over C is Q1 over C1 plus Q2 over C2, right? So if I know, also I see that the charges are the same, so I can cancel that, and this gives you the very famous formula that you've seen many times in your homework, that if you combine two things in series, right, that's the equivalence capacitance. This one I do memorize, right? The others I don't, because, so my advice to you is this basically summarize everything I need to, or most of the things you need to know about calculating this capacitance. All right, number 1, learn how to draw this diagram. Number 2, learn how to extract out these informations from the diagram. Okay, if you master this, you're 80% of the way in understanding all the things. The only tip I'll give is to further solve the problem, use the definition, plug it in, and then usually you can generate all the other information you need to solve the problem. Let me provide you one more equation about capacitance. Is the energy that you stored inside a capacitor. Unfortunately, I don't have time to go through like I just did to explain where that comes from, but that's the amount of electric potential energies that's stored inside. There's 3 versions of this. You can remember this version, you can remember this version. By plugging this definition in the capacitance, you can eliminate the C. If you like, you can eliminate the Q as well, like this. So it's up to you. I won't memorize all 3. I will pick one of your favorite, and then, for example, pick the second one, pick the third one, pick the first one, and then remember you can replace this inside. Okay, all right.